we're going to talk about storing energy, the different ways energy is stored up. We'll review kinetic energy, because we've already talked about that. And then we'll introduce gravitational potential energy and elastic potential energy. These are ways of storing energy by placing an object at some position in space or something like that. And then we'll have energy bar charts. And energy bar charts are a way, it's a diagram looking at work and energy and that sort of thing. So let's get started. Now let's talk about how energy is stored in kinetic energy. Okay, now we've already defined kinetic energy, right? We said kinetic energy, K, is equal to 1/2 the mass times the velocity squared of an object. And really what this is a measure of is how much work an object can do because it's moving and has velocity. How much change can it make to its environment? Now, here I have a baseball. Okay. Now, let me try this. Okay. Now, if let me zoom all the way out here. Now, if I put, I don't know if this will work or not. We'll see. If I put my face right next to the ball, right? If I can do this. Now, can that baseball do any work on my face? No, it's just sitting there. It doesn't have any energy with respect to my face. It's not going to plow into it. Now, one of my former students is named Garrett Olson. Graduated many years ago, and he became a major league pitcher. Pitched for the Orioles and then the Mariners, or Seattle Mariners. I think he's still. Anyway, what if he grabbed this baseball and threw it at my face as fast as he could? Like, let's say 100 miles an hour. If this baseball was moving at 100 miles an hour, could it do work on my face? Yes. It can change my face's environment severely. Okay, bones will crack. Flesh will be crushed. Maybe brain tissue will be smushed. Okay, that's a change in the environment. So because this thing is moving and it has mass, that's when it can do work. That's when it can affect change into the environment. So it's kinetic energy. Gravitational potential energy. Okay, now this is when energy is stored up because of an object's position in Earth's gravity field. If I took this baseball and I carried it to the top of a cliff, or let's say maybe the top of a building, right? So here's that baseball, and this has a certain height above the ground. And let's say here's an unfortunate soul standing beneath, at the bottom of this building. If I drop the baseball, can I do work on this person down here? Can I change their environment? Yeah. If I release the baseball, gravity will do work on the ball. And actually what it will do is it will change the energy from gravitational potential energy to kinetic energy. Now, energy is just energy. There's just different ways of storing it up. You can store it by lifting it up, and then gravity can do work on it and change that energy into kinetic energy, and then the kinetic energy of the ball will do work on the head of this person or the toe or something. Okay? And so what gravitational potential energy is the work gravity can do because an object has height. Okay, it's the work gravity can do on an object because the object has height. Well, let's figure out how much work gravity can do. This is at a certain height. Now let's hold the baseball over the edge of the cliff right here, and then let's just release it. So gravity's going to do work, and gravity is going to go down, right? And the displacement, and what is that? That's mg, the mass of the baseball, times 9.8 newtons per kilogram. And then it's going to fall down, right? There's my delta y, my displacement. So what is the work that gravity can do? W sub g, the work of gravity. Well, what's the force? mg. Now, what's the displacement? Delta y. What's the angle between the displacement and the force? No, it's not 90. Look, what's the angle between the weight and the displacement? The weight is down. The displacement is down. What is the angle between down and down? It's 0. What's the cosine of 0? 1. All right, so this is just going to be mg times delta y. But what I'm going to say is that the height the object has, instead of calling it delta y, I'm going to call it h. So this is how much work gravity can do. Because this is the force and this is the displacement. And the angle between the force and the displacement, if you drop it, is going to be 0. Now we have when energy is stored up in a gravity field, or because of its position in, later on we're going to talk about electric fields, and in a few minutes we're going to talk about elastic potential energy, but when it's stored up due to an object's position, we call that potential energy, and we use the letter U instead of K. K is for kinetic energy, but we use the letter U for potential energy. I don't know why we don't use capital P, although it's used for power and so on, but it's just tradition to use capital U to represent potential energy. Don't ask me why, because I don't know. So U sub G, gravitational potential energy, is equal to mgh. And that's the equation that we use to represent. And it has units of joules. Okay. Now we're going to talk about elastic potential energy. Well, have you ever stretched a rubber band and then shot it at a friend, or someone who wasn't a friend, or soon to be not a friend? Okay. Sure you have. Okay. Or have you ever taken a ruler like this, and then you bend it, and then you let go of it? Okay. Here's my friend's face, represented by the baseball, and I'll take this ruler, and this ruler has no energy stored in it. It can't really make any changes to its environment. But then I pull it back. Now who's doing work when I pull it back? I'm doing work, and all that work is stored up now in the bent ruler. If I release the ruler, now the ruler can do work on the ball. Bam! Okay? I released energy. I used energy to smack into the ball. Okay? So, elastic. What does elastic mean? Well, it means something is stretchy or compressy. Stretchy or compressy? Okay, sorry. Elastic potential energy is the work a stretchy material or springy would be a better word, maybe stretchy or springy, material can do because it has been stretched. Like a spring, you can stretch a spring, or compressed, or bent. Like when I bent the ruler, I was storing up energy because it's been bent. And that is called elastic potential energy. Now we're going to do a little lab later on where we're going to develop an equation for elastic potential energy. So I'm not going to give you that equation right now. There is an equation. Okay, it's 1/2 kx squared, where k is the spring constant. But, you know, it's just like a bow and arrow, right? You ever shot a bow and arrow? You ever go up to, like, you know, camp, Girl Scout or Boy Scout camp or something where you shoot a bow and arrow? When you draw that arrow back, you are doing work. You're applying a force through a displacement. And work is when you transfer energy out of your body into something else. So you put work into that bow. That bent bow now is storing elastic potential energy. When you release the arrow, the bow does work on the arrow, applies a great deal of force through a displacement, and transfers its energy into the arrow. The arrow now has kinetic energy, and the arrow can, you know, shoot into a target, or, you know, a poor little bunny rabbit or something. Whatever you know, whatever it hits, it can do work on it. It can affect change. So, but it all comes down to energy. Now, I can. I'm going to show you a very simple situation, and we're going to look at it in terms of these forms of energy and of work. So we're going to, you know, kinetic energy, gravitational potential energy, and elastic potential energy. I'm going to give you a situation, and what we're going to do is we're going to draw a bar chart to represent it. So what I'm going to do is, here's the ground, and in my little thought experiment, I'm going to throw a ball essentially from the ground. Let's say that the height of the person throwing the ball is insignificant. I'm going to throw the ball. The ball is going to go up and down, and then it's going to hit a spring, and it's going to squish that spring in and stop. Now, maybe it'll bounce off the spring and go back up. Okay, let's just do that. Okay, and this involves kinetic energy, gravitational potential energy, and elastic potential energy, all in the same problem. Well, let's say that the ball starts here at the bottom. It's not moving. It doesn't have any gravitational potential energy, does it? So I'm going to put a empty part right here. This is going to be kinetic energy plus gravitational potential energy plus elastic potential energy, okay? Now I'm going to do work. The thrower of this thing is going to, here's a person, and they're going to bend down and throw that ball straight up. They did work. They transferred energy out of their body and into the moving ball. And what kind of energy did it have as it left their hand? Moving very fast straight up with all that mass. It's got kinetic energy. So what you have to do is you have to pour energy into it. And I want you to think of this as almost like a container that fills up with kinetic energy as you throw the ball until you get to your maximum kinetic energy. And now the ball has kinetic energy. But what happens to the speed of the ball as it goes straight up? It decreases. So we're losing kinetic energy, right? Why is that? Because gravity is pulling it down. Gravity is doing work on the ball. In fact, gravity is doing negative work on the ball, right? Because if we draw a free body diagram of the ball right here, the force of gravity is down, but the displacement of the ball is up. So gravity is doing negative work. We're taking kinetic energy away, but as the ball goes up, what are we gaining? We are gaining gravitational potential energy. So here's my gravitational potential energy container. Okay? Now, as the ball goes up, energy will be transferred from kinetic into gravitational. And these little lines right here, this represents the work done. This is the work done by the person. This is the work done by gravity. And when gravity does negative work, we gain gravitational potential energy, right? This will go down, and I wish I could draw this as a cartoon, you know, in motion. Maybe I can find one on YouTube or something. But this empties out, and when it reaches the very top, where is all my, all this kinetic energy is gone, and when it's at the very top, all of the energy is now gravitational potential energy. Okay? Now we still don't have any kinetic, well, we have no kinetic energy at the very top. We still don't have any elastic potential. I know the spring is just sitting here. There's no energy stored in it. Then the ball starts to fall. For an instant, it has zero velocity, zero kinetic energy, but then it starts to fall. And look, gravity is still pulling on it. Here's my gravitational force. And now what's the direction of my displacement? It's down. So the force is down. As it falls down, the displacement is down. And now gravity is doing positive work. When gravity does positive work, we lose gravitational potential energy. But what happens to what's happening to the ball here? What's happening to its energy? It's turning into what? Back into kinetic energy. So gravity's doing positive work now. See, here it's negative work because we're adding potential energy. But now it's negative work. We're removing positive work. So we're removing gravitational potential energy, and we'll slowly fill up well, not slowly, fairly quickly, it'll turn back into kinetic energy. Am I still on screen? Yes. Okay. So now, this gravitational potential, let's look at the ball just before it hits the spring. Well, there's a little bit of height left, so there's a little bit of gravitational potential energy left, but almost all of the gravitational potential energy has been turned back into kinetic energy. Okay? But then it starts to hit the spring. And what happens to my energy when it hits the spring? It compresses the spring, it pushes it down. We're doing work on that spring, and that work is storing energy in the spring itself. Did you ever have one of those little dart guns where you press a little dart into the gun and you compress the spring? You did work, right? You had to push that little dart into the gun. You compressed the spring. All that work you did is stored up now in that compressed spring, and that's elastic potential energy. So let's look at the ball right here. The spring is completely compressed. So here's the ball. It's completely compressed, that spring. So Gravity did a little tiny bit of work as it was compressed down, but we lost all this kinetic energy. I mean, the spring stopped the ball, and so now all the energy, you know, we lose the kinetic energy and it all gets stored up in there. So this bar chart is a way of looking at what happens to energy in a system where energy is being transferred from the outside the system. You did work, gave the ball kinetic energy, the ball went up, we gained gravitational potential energy, the ball came down, the gravitational potential energy turned back into kinetic energy, and then we compressed that spring, and all that energy became contained in the compression of the spring. Now this is going to lead us to our next big concept, which is a conservation of energy. But this is what's going on, and this is a very nice model. You can kind of think of energy as this, almost like a fluid-like substance that gives you the capacity to make changes in your environment, but you can change the way it's stored. You can store it in the motion of an object, you can store it in the position of the object, in where it is in a gravity field. You can bend or compress or stretch an elastic material and store that energy there. Or like we did in the starter problem, we can store it in the random motion of molecules, you know, that we call heating, which we're going to study later on. Okay, so that is what you need. Now, hey, for homework, work the example problems. We didn't have time to do that in class today, so work the example problems and then do the practice problems that have been assigned. That is it. Have a nice lunch.